Hi guys, my name is Vinayak Borkar. I'm the CTO and VP of Engineering at X15 Software. It's a little startup. We do machine data management. I'll kind of describe very quickly what we do and then get into the meat of my talk. First out of one, late binding means a lot of things to a lot of people. I'm going to focus on what late binding means to us and specifically in the context of the kind of work we do. So here is a kind of an overview of what X15 is. X15 is a machine data platform that starts with ingesting, streaming machine data. Machine data is basically log data, if you will. We collect that both in streaming as well as batch, and ingest it, index it, and store it. So that it can be analyzed later. We also provide visualization and monitoring, and all this happens in a scalable manner on top of HDFS. There are a whole bunch of features. I'll probably not walk through all of them, but the idea here is throughout the talk, you'll kind of see what log data translates into. It's essentially semi-structured data, so you don't know upfront what it is that you're going to get. One of the things that we do is we index it both for full text search as well as database style lookups. In addition to that, our belief is just because you move into the semi-structured world doesn't mean you have to throw out SQL. In fact, there's a great paper from UCSD, from Yannis Papakonstantinou, called SQL++, where they talk about how to extend SQL to provide semi-structured data access, or you be able to use SQL for accessing semi-structured data quite naturally. So there are massive advantages to be obtained by sticking to the SQL ecosystem, just because there are lots of products which know SQL. So very quickly, let me talk about what machine data is. A lot of you probably already know this, but machine data, basically log data, is a capture of events as they occur. And machine data, log data is generated by pretty much every device, every application that is running around us. So some of the events could be results of human interaction. So somebody clicks on a web page, that creates a weblog. Somebody sends an email, that creates an email log entry somewhere. It could be a result of non-human activity, sensors that are collecting temperature data, or any kind of metrics off of networks, and so on and so forth. So machine data basically originates from a whole bunch of different possible sources, and the advantage, the use cases for machine data are enormous. So there's a whole bunch of different use cases that are served by collecting and analyzing log data. I won't go through all of them, but there's a couple of customers that we have. Essentially, it turned out that log data was not only useful for, so traditionally one thinks of logs as being useful for application developers when you capture application logs and look at what kind of errors are showing up, or what performance metrics look like for your application. But it turned out that the application logs were fairly useful to other people in the company because, for example, marketing was trying to understand the usage of this SaaS application, and looking at logs was a great way of figuring out how people were using, how their customers were using this data. So here is an example. I mean, a lot of you probably are familiar with what weblogs look like. Essentially, they are strings of text that contain pieces of information embedded in there. Here is an example of Linux security log. Again, captures information such as invalid logins and so on and so forth. There's a timestamp. There is information about which host this happened on, process name, process ID, and so on. One thing to note is log data always pretty much has a timestamp associated with it, and the sequence with respect to time is absolutely relevant. Log data also contains session information. So for example, the log entries that are marked here are actually part of one session where somebody tried to log in with an invalid ID, but those log entries are multiplexed with other log entries that perhaps do not belong to the same session. Here is an example of an application log. Again, logs do not have to be single-line records. You can have multi-line log records, again, which contain different parts of, which contain different facets of information. One thing to note here is this system that we build at X15 is very different from the previous talk we heard, right, MongoDB. MongoDB is built for OLTP, for basically maintaining application state within the database. X15 is in the business of recording history. So the difference is we are trying to mirror what is happening in the real world, right? So from an ingestion standpoint, it does not make any sense for X15 to have, or for that matter, any log collection system to have constraints to say that something should look a certain way before getting the data in, because you're recording history, you better record what happened, and the constraints are already satisfied by the real world. So machine data analytics usually starts with, as we saw in the previous picture, data collection, some kind of data normalization. As you saw, the logs look fairly textual, but then there is information in there. So you could call it parsing, you could call it extracting metadata, and then you might choose to index and store some of that data. And then you go into the analysis phase. Except when you start doing this, you kind of sometimes need to go back, because when you start doing an analysis on the logs, you might encounter, you might realize that not all structure was extracted, or certain structure that is relevant to the analysis at hand has not been extracted. So you go back, perhaps redo your parsing or extraction of the metadata, or you might even decide that there is some other piece of information that needs to be fetched, which has to be viewed in the context of the analysis being performed. So data normalization or parsing is basically the act of taking something like that, which is your log entry, and translating it into key value pairs, for lack of a better term. And as you can imagine, logs, just because every log record could have different types of information. I mean, this is Weblog. You could have, for example, cookie data, which is just a bunch of name value pairs, and whatever name value pairs an application decided to embed into the cookie, you could end up with a variable number of name value pairs coming out of these, when you parse these log records. So one thing to note is, I mean, there's no right answer to parsing. Any parsing you do at best is perhaps going to capture some of the information that you probably knew about from the log, but there's always going to be something in the logs that you don't know at the time of parsing, or it is possible that in the future the log format might change, in which case the parsing that you perform is not really extracting all the structure that is present in the log data. So what do you do in such a case? Right? One other piece of part of data normalization is data enrichment. So for example, we extracted key value pairs like this, but in order to start doing analysis, perhaps it might be useful to know what HTTP status 206 means. What we captured as the URL might be, so it might be useful, for example, okay, here I have an IP address. It might be useful to say, find out what the specifics about this IP address by doing a GeoIP lookup. So this IP address turns out to be from Beijing, and so on and so forth. Similarly, you have a user agent here. The user agent pretty much has every browser's name in it. So which browser is this really? So you might want to use an API service to figure out which browser this request actually came from. Finally, here I have a URL which was captured as one name, but turns out that I could perhaps look at the URL as two parts, path and file. Now, depending on the type of analysis you do, it might be relevant or it might not be relevant, right? So there's no way for the person trying to build parsers, in isolation of the analysis to know what kind of structure to extract. So just to summarize, parse data may be enriched using a few strategies, right? So one example is perhaps looking up a site table. So 206 maps to partial content, and that could be a lookup table. Lookup using API for the user agent, for example, or just transformation to break URL up into path and file, right? There's just three classes of, three examples for how data enrichment could be performed. So the challenge with machine data is it's amorphous in nature, right? Looks fairly textual, has no clear schema. The raw data itself is immutable because we said we are recording history, right? History does not change. But the interpretations might change. Parsing out all the fields is hard, if not impossible. Which fields are relevant depends on their use. As log formats change, parsers may not be parsing what you thought they should be parsing. And so the general idea is you would probably want to extract some structure before storage, but there would be on-the-fly structure extraction as you're doing queries, right? And similarly, as we said, we also want to enrich the data by doing dynamic lookups and so on. So the question is this: are there any optimization opportunities here, or are we stuck with a slow system just because we have no schema? We have, and if you look at classic database style research, it is focused pretty much on structured data where schema was very well understood, types were well understood, it had all the integrity constraints that you can think of, and you got good performance out of the database when you started doing analytics. In the last few years, we have seen some effort in optimizing performance of systems that manage nested data, but not semi-structured data, right? Nested data, so Google Dremel basically describes how they map nested data into columnar storage, so you can analyze things faster, but they still assume that the schema is known. So the question is, what can we do for machine data? So just to kind of iterate how a log management platform perhaps works is you have data coming in from different types of files or different types of inputs that is streamed in, and structure is perhaps extracted. Sometimes structure is inbuilt. Like for example, the JSON file is self-describing, so it says this is my structure. Sometimes you get logs, in which case you need to extract the structure. But regardless, you can think of it as some structure is extracted before indexing and storage, and some structure will have to be extracted after the fact when you start doing the querying. So let's look at the first part of structure extraction, the ingest-time structure extraction, right? I still refer to this as late binding. I call it type 1 late binding. The reason I call this late binding is when you created the store, there was no mention of a schema. Unlike in a traditional relational database where you start with the schema, so one could say when the data comes in, you already know what to expect. Here you do not. So what we said is some parsing is applied prior to indexing. So here I have an example. This is actually a Cisco ASA firewall log record. In fact, specifically, this has to do with setting up a TCP NAT connection from this public IP or this private IP to that public IP. So again, there is a timestamp, there is the device host, the type, it tells you a Cisco ASA, and then there's a message. So one could perhaps parse this as, so I'll come to the raw in a moment. There's the timestamp, there is the device IP, the source, and a message, right? So something as trivial as this could be parsed out when the data comes in. However, remember we said that not everything is being parsed. Perhaps even this interpretation of certain things may not be what the user might have wanted to do while querying. So it's always safe to keep the original raw data in there. So in our data model, we basically keep the original raw data and we extract whatever structure the parser perhaps extracts. Now, these are the index time index time fields that have been extracted. Now, let's closely look at these logs, right? So what you'll notice is the highlighted entries read very similar, right? So invalid user admin1 from some IP, invalid user admin from some IP, invalid user ale from some IP. So the idea is, if you look at a log file, essentially it's multiplexing of a whole bunch of log types. And if you really think about where do these logs come from, I mean, here is another set of logs which look very similar. Failed password for invalid user admin1 from so-and-so, port so-and-so, and so on, right? So at the end of the day, the number of, so where do these logs come from? Logs are, at the end of the day, generated by applications through use of some template, right? So there's some template behind the scenes which is generating a log file like this. So for example, it probably looks like this. Failed password for invalid user, some parameter from, some parameter port, some parameter protocol, some parameter, right? So what this means is, although there are different types of logs, there are only so many generators for these logs, right? So the question is, can we exploit this property somehow to optimize what we want to do with machine data? So let's look at storing schema-less semi-structured data. So the fact that there are relatively few generators or templates that generate these logs probably means that there are a few schemas that describe the log entries that you see on a day-to-day basis. Right? So the question is this: during ingestion, can we try to extract the schema at an instance level and merge similar schemas, right? So here we are not trying to actually reproduce what the schema was in the form of, in fact, we are not trying to figure out exactly what the template was that generated the schema. What we are trying to do here is, there are many right answers. You can extract at a schema level, at an instance level, the schema, and merge schemas that are similar in nature so that you can separate out the schema from the instance and describe a whole bunch of, a subset of the instances using one definition of a schema. So you end up with essentially a bunch of what we call as classes of records, if you will, right, that have different schemas. So, for example, in the previous case, you can essentially think of, there is a schema for failed password for invalid, where perhaps by basically looking at the similarity between these, you can figure out that failed password for invalid is probably a string that repeats in each of these, and hence probably they belong to the same template. And then the user admin1 here, admin, and ale are parameters passed to that template, right? So if you look at logs collectively, you end up with a few what we call as classes of records, where the subset of logs are described by a particular schema. But the schema, remember, is extracted from the data. So this may not be the actual template that generated this log record. Now, since there are far fewer classes of records than records themselves, we can now think of specializing both storage as well as processing for these different classes that we have observed, right? In fact, you could think of a structured relational table as a special case of a multi-class strategy like this, where there's exactly one class and you know it up front, right? But you can derive that from the data. In fact, you can derive that using unsupervised learning and use that for storage. And in a moment, I'll describe how we use it also for query optimization. Let's look at the other type of late binding, which is query time structure extraction. So let's go back to our original record, except this time, remember in the message field, we had outside : IP port, inside : IP port. Let's say we want to further extract fields from the record where you have, I mean, in this case, it is key : value. If it was a proxy, if it was an HTTP log with cookie information, it would have been key equals value, and so on and so forth. But we have functions where in X15 called extract KV, which accepts regexes for keys and values, and can basically apply that to a string and extract fields. So for example, when you apply extract KV with the right regexes for key and value, you would end up with a record like this, which says outside is this field, inside is this other field, right? So you can use functionality like this to do query time structure extraction and process this data as if these fields just existed in the original data. Now, the problem is this. Let's say now that you have fields over computed, you have filters over computed fields. So I say extract this inside and outside, and now I have a filter condition on outside, right? Traditionally, if you do this with a database or any technology that we've seen, you would end up essentially with a full table scan, right? So imagine there was a condition which said where record of outside equals this constant. However, what we are able to do, because we kind of know how this was extracted from the text, we can now take this condition and turn it on its head. So in other words, we push the predicate through the function that was used to generate this, and essentially end up with a condition on the raw record that looks like this, right? I mean, this is one example, but this works for a whole bunch of different cases. So you end up with conditions being pushed back, and now if raw was indexed, this is essentially an index lookup, right? More importantly, sometimes this push down through these functions tends not to be exact, but through some query relaxation, we can actually push a condition that brings in a slightly larger set, but is still far more optimal to fetch than applying just the condition, in which case we do the original condition as a post evaluation. But queries basically go from being table scans to index lookups at this point, right? So did not compromise on late binding, did not compromise on the fact that X structure is extracted during querying, but you still get the benefits of having extracted the structure beforehand. Final optimization that I want to talk about is, this is runtime optimization, which is, so traditionally in a semi-structured database, when you have queries and because you do not know the schemas up front, you end up with a lot of code that does dynamic dispatch, right? What is dynamic dispatch? So you end up with, so let's say for example, I have a construct which says record of X plus record of Y, right? Where plus is perhaps an overloaded function. So if it's integers, it's going to add up integers. If it's integer and double, it's going to do integer plus double, and so on and so forth, right? If it's two strings, it might perhaps concatenate those two strings. So given that we don't know the data types of X and Y in a traditional semi-structured database, your plus operator at runtime essentially is a big switch, which says look at the input left type, look at the right type, and decide which part of the code to jump to. This is not the best use of what modern processors are capable of. Again, applying the same kind of looking at the data similarly as we saw before, there are only a few different types. In fact, when we ingested the data, we collected the record classes, the schemas that we inferred. So as a side effect, you know what combinations of X and Y exist in our data, right? So what you can do now is create specializations at compile time of the query for interesting combinations of X and Y. So instead of having a runtime dispatch, you have a compile time dispatch based on record classes. And here's a little, it shows you kind of the performance difference in basically just specialization. In fact, so here, let me just walk through. So the x-axis here represents the number of actual record classes that appear in the input. And the y-axis is the time to perform a plus operation in nanoseconds, right? And you see that with dynamic dispatch, regardless of how many classes you have in the input, it's around the same time. It hovers somewhere between 1200 and 400 nanoseconds. On the other hand, by specialization, if there is only one class, it essentially performs as well as it would in a relational database. And it still keeps performing well in spite of, at some point you see a little bit of jump. I think this is because of the instruction cache, because the specializations become so many that the instructions go out of instruction cache. But for the most part, you see that it still performs better than the dynamic dispatch. And so you can pretty much get the same performance that you would with a relational database with schema on read and late binding, right? So this is my last slide. So oops, I guess. Okay. In conclusion, amount of machine data is just growing. So and traditional database techniques do not work well because of the semi-structured nature of the data. Using a general purpose semi-structured database adds too much bloat because you store all the name values and so on and so forth, and it doesn't optimize for this repeated nature of the record classes that we discussed. So we believe that you need a purpose-built storage and query engine for processing machine data. You need MPP capabilities so you can scale, but you also need optimizations like the ones we described so that you can get raw performance that is actually scaled using an MPP platform. And yeah, thank you.
Any questions? There's a latency. Oh, he has one.
It sounds like you're doing a lot of work to infer schemas from places where there is already, as you say, because these log messages are generated by templates, there is already sort of an implicit schema there to begin with. Isn't there some way that we can have that implicit schema communicated to the end analysis tool? If they just dump those templates in the file at the beginning or something like that, then we could
that would be
not
great.
have to do this.
Yeah, that would be great. Unfortunately, I don't think we can tell Cisco to have a schema as part of their log file. But the truth is, once you start going after these use cases, you find that it's kind of a 90-10 rule, right? You could argue that some of these devices are fairly fixed and their schemas are well known, but then there are applications which are developed by programmers, and most of the time the logging is added for human. For reading, by humans, and that keeps changing release after release because they are trying to debug something, the structure of the code changes, so having somebody communicate the schema in addition to the logs themselves, there is no practice. And usually the person who is generating the logs is not the person analyzing them. Or maybe the person analyzing them, but there are many more people who are analyzing logs than the person who actually wrote them.
So have you thought about having like an open source adapter model?
Sorry.
Like having some sort of open source adapter model. So, somebody writes an adapter for their particular switch or their particular web server, or
right?
Because it's almost like this needs to be crowdsourced.
Absolutely. So I think again, as I said, there is the 90-10 rule, right? So 90% of logs probably come from standard devices like routers and so on, which you could probably crowdsource. But what about application logs that are specific to the company who's building the application? You end up with a lot of log data from applications that are just private, and there's no crowdsourcing opportunity there.
Except for the developers that are developing the application that want to be corporate citizens, that want to be good citizens.
Yeah, so there are two parts here, right? One is the transporting of the logs. So that, I think, has been fairly standardized. So there is syslog, there is, in the Java community, there is log4j or a logging framework. So moving the logs from one place to another, that's fairly well understood and taken care of. I think the problem is communication of the structure.
So we have time for one more, so go quickly, and we'll.
So we've got a pipeline with a whole lot of logs in it, and we get fragmentary and damaged logs from time to time. With your automatic schema extraction, is that going to pollute your auto schema and cause all kinds of havoc?
Yeah, so we have actually seen, so we've used, okay, so a related thing is once in a while what happens is logs, they get truncated, but more importantly, the line delimiter between logs vanishes. So you end up with a really, really large log record, and if you try parsing that, you end up with essentially bringing down the server, right? So one thing we found was, again, through unsupervised techniques, you can actually figure out what the average size of a log record is. And we can actually automatically say, at some point, that this is an invalid log record. So that, we have not tried it with truncations, but perhaps a technique like that could work with truncations too.
Okay, thank you so much. That was cooler than an X15, so.